we are now going to take a look at proof by contradiction and counterexample. A proof by contradiction is built on the logical reasoning that if a proposition is true, its contrapositive is also true. These are a lot of notations. This means like not. This is if and only if. But essentially saying if A implies B, that is the same thing as saying, well, not B is not A. A nice example to illustrate this, make a lot more sense. If x equals 2, then x is even. Super easy to understand that. It also implies, though, that if x is not even, that x can't be 2. There's no huge leap in understanding to realize that these are true and logical consequences of each other. In a proof by contradiction, we're going to first identify what's being implied by the statement and assume that this implication is false. Then we're going to do some math, blah, 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 axioms, theorems, definitions, properties, to arrive at a contradiction. And because that's a contradiction, we've proven that the original statement has to be true. We're going to show that the square root of 3 is irrational. And we're going to do it by assuming that it is rational. So let's pretend we're going to assume that the square root of 3 is rational. I'll try to write neatly and that you can read it, but there's always a lot of writing in these kinds of proofs, so I hope I don't take up too much space or get too messy here. Remembering back to the time before, if something is rational, that means that it can be written as two co-prime numbers, so reduced p over q, for example, that are elements of C. So that means then that you can write the square root of 3 as p over q, where they are both elements of the integers, and p and q are co-prime, which means they have no common factors. So what we can do from there is say, well, that must mean if the square root of 3 equals p over q, I could square both sides and say, well, 3 equals p over q squared. So 3 equals p squared over q squared, multiplying. As you start doing these proofs, it's not always easy to see how you want to proceed. As long as you keep making logical truths, and you're building bridges towards getting somewhere, and you may have to go back and edit, just like you're writing an essay, and say, okay, what are quicker ways I can get there? What's the most concise way? There are different ways to prove things. You'll see patterns that emerge over and over again, irrationality, writing it like this. So there is a lot of experience that comes into this where you just have to practice building it. It is tricky. It's not something we do a whole lot. Yeah, it's not as straightforward necessarily as some of the other things that have a simple formula or a simple pattern, but just doing practice is going to be the best possible thing to get comfortable with these. Okay, so what this means though, this means that 3 divides p squared, so you could say p squared is equal to 3 times k. That would be one way. You could also say 3 divides p squared. And there is a property, and this is something you just have to know. It also makes sense logically. This implies that 3 divides p. Thinking about it a little bit logically, it's like, imagine you have the square number, let's call it 49. That's a bad example with 3. Let's call it 36. If you break down 36 into its prime factors, and this is only true for prime numbers, if you break it down and you know that 3 goes into 36 as a prime number, then it must go into its square root, okay, which is 6. That's not true, for example, and you'll see it actually in my counter example, if you have a non-prime number, because it could be split into its prime parts in different ways. So 4 goes into 36, but 4 doesn't go into 6 because we have the 2 and the 2. So only for primes, but there is an axiom that says this, a law. So another way we could write that, though, knowing that 3 divides p, is that p is equal to 3 times some integer. These are things that come up a lot. And if you know that 3 is equal to some integer, then you can write that 3q squared equals p squared is equal to 3. So 3q squared equals 3k squared. I'm going to now go up here because of the sake of space here. I could then say, well, 3q squared is equal to 9k squared, and dividing it out is equal to 3k squared. But that also means that 3 divides q squared. Okay, so 3 divides q squared, but that also implies that 3 divides q for the same reason of the primes. But we said, here's the contradiction, but we said that they don't share any common factors, that they're co-prime, that p and q are co-prime. They don't share any common factors. This is a contradiction. Do the thinking for them, write the statement. This is a contradiction. Hence, the square root of 3 must be irrational. Okay. And that we have done. Here's another example, a much simpler one. Proof by contradiction. Prove that there is no x in the real numbers such that 1 over x minus 2 equals 1 over x, 1 minus x. Let's pretend there is. Assume that there is an x, that there exists, okay, an x in the real numbers such that 1 over x minus 2 equals 1 minus x. And if there is, then we can solve it and we can find it. So then I'm going to use the laws that I know already in mathematics to say, well, I'm going to multiply by x minus 2. 1 equals 1 minus x times x minus 2, which would imply that 1 equals, and I'm going to just factor this out. So x minus 2 minus x squared plus 2x. And just keep using these logical steps. To simplify this, I'm going to move things into a common order here. Negative x squared plus 2x plus 3x minus 2. This is nothing hugely surprising. Okay. Minus 3. And then I know I can solve this using the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac, okay, all over 2a. Hopefully you're able to see this. And if you simplify this, you may already see it. This is going to be 9 minus 12, okay, all over negative 2. And that's going to imply that x, and this is where you just have to be really pedantic, negative 3. But this is not a real number, okay? But this is not an element of the real numbers. You can cross that out. That's actually the correct notation. I'm not just crossing it out because I made a mistake. So this is a contradiction. That means that there is no x. Our original premise is true. There exists. You could write it like that. You could also write there exists out no x in the real numbers such that 1 over x minus 2 equals 1 minus x. And with that, we would be done. A very simple and final kind of example of contradiction is just using a counterexample or a counterclaim. It's an acceptable form of proof that proves a given statement false just by proving that there's one example where that's not true. So to prove something true, we talked about it in TOK, you need to prove that it's always true. But to prove it false, all you need to do is give one justification that it's not always true. So, for example, show by counterexample that if n is an integer and n squared is divisible by 4, then n is divisible by 4. This is not true because, for example, all you have to do is think of one, and there are a whole bunch of them. Let n equal 6. N squared is 36, which is divisible by 4. Don't get too caught up in the mathematical symbols, which is divisible by 4. However, 6 is not divisible by 4. So this is not true. And that's how easy a counterexample can be.